Good morning, everybody. This time let's look at a simpler setup. It's a similar problem to last time, but this time we're going to use the Black and Scholes formulation of this problem. And that's nice because it's easy. So here's our assumptions. There are only two assets in the economy. There's going to be one safe asset, like a bank deposit, and one risky asset, like a stock. So no more matrices, which is nice. I was making all kinds of errors with transpositions and matrix multiplication. We don't have to worry about that anymore. There's going to be no consumption, there's going to be no state variables, and there's going to be no labor income. And also no time discounting. So the only thing this agent's going to care about is to get as much money as possible before he dies. He just wants the high score in life. So what are our assets? As always, the safe asset is just going to be defined as the risk-free rate of return over time. And the risky asset, we're pretty much always going to make a geometric Brownian motion. So mu t dt plus sigma t dzt. And the first question we always have when tackling one of these problems is, what's the wealth function? What's the wealth function? So let's define pi to be a percentage of wealth invested in risky, so that pi w is the amount in the market. And then 1 minus pi w, then these are t's, and everything's t's. 1 minus pi w will be the amount in the bank. So at every second, our agent is going to decide how much money to invest from his bank account into the stock market or to pull out. So it's going to be a dynamic decision to invest in this one risky asset or risky portfolio. So their wealth then, remember they can't work, they can't consume, so they get their risky returns. That's going to be given by the amount they invest times what they get, their returns, which is given by this diffusion process, plus their safe assets, the amount of interest that they get on their bank account. So let's gather the dt terms. So we have mu t minus wtrt plus, I'm sorry, this one is minus, the other one's plus. I can't use my it's late excuse anymore. I gotta get my game together here. Pi t wt rt, and all of this is dt. And to that we add the dz term, which will be pi t wt sigma t dzt. Okay, and we can do a little bit of cleaning up in here. Factor out a w first. So we're left with pi t mu t plus rt minus pi t rt. And then looks like we can factor out a pi t from inside of there to make it just a little bit easier. Excuse me. Alright, so we're going to end up with rt plus pi t mu t minus rt. Very good. And that is our wealth function. And that's always where you want to start these questions. How much resources does this agent have at all times? And once you know that, then you're halfway there. We'll even put it in a nice orange box. So that was pretty quick. Let's just power on and we'll get our Bellman equation. So in this case, remember that there's no consumption. So this person only cares about maximizing lifetime wealth. And there's no state variables, so this function will be a function of w and t. It's going to be the maximum, and they're going to maximize their portfolio at every time t, such that the utility that they get at the terminal date is as high as possible. And what that's going to amount to is at every point t, what is mt? At every point t, they're going to rebalance their portfolio over their whole life, t, such that their wealth at that time is maximized. Okay, and we don't know how to solve this problem. This is the forever problem, but we know our little trick. We know that we can crack off a tiny bit of the problem. So let's do it. This is exactly the same as saying, well, let's split this integral. Let's split this integral into an integral from 0 to delta t, ws ds. And then to that we add what's left, the delta t to big T, ws ds. And then, this is kind of hand wavy, but we can sort of evaluate this function and say, well, this will just be s w dt, or sorry, sws evaluated from this dt to 0. And I know this isn't rigorous math, but it's kind of what we can think about it. So we'll get delta t, w, delta t. We can enjoy that little bit of wealth we accumulate over this time for this long. And then we would subtract, 0, w0, which just goes away. Again, a bit hand wavy, but don't complain when it's one day before the test. All right, delta t, w, delta t plus, and now we're going to realize that this is exactly the same as this, just shifted a little bit. So let's just write this as j w t plus delta t, t plus delta t. And then over here we have our j w t. Now if you watch the other video, you know now our objective is to take the limit of this so that we can make this delta t the smallest delta t possible. We want to take the limit as delta t goes to 0. And furthermore, we know that the diffusion mu j is defined as 1 over delta t, as the limit as delta t goes to 0 of 1 over delta t times the quantity j w t plus delta t, t plus delta t, minus j w t. And so clearly from the pieces we have here, we can set this up. We can rewrite this equation so that it's 0 equals max pi t. And then we'll divide everything by delta t. So here we just get w delta t plus 1 over delta t, and then the thing that we want, j w, a little derpy, w t plus delta t, t plus delta t minus j w t t. This is also in expectation. There should have been an expected here all along. But I'm being very sloppy. It just ends up getting dropped anyway after Ito's lemma. But I apologize for the sloppiness. Don't drop that on the test. That's probably bad. So starting from like up here, this is all in expectation. Okay. So we apply our limit operator. Limit as delta t goes to 0, and the limit of the sum is equal to the sum of the limits. We can distribute it over addition here and here. So we're going to end up with 0 equals the max of pi t plus and then some initial condition w0 plus, and now we know that by definition this is equal to our mu j, which is the drift term of the j function. So to recall, this is the drift component of j. And you say, well, where does the stochastic component go? The stochastic component is wiped out by this subtraction. So there's a dz in here, there's a dzt in here, and there's a dzt in here. And as t gets smaller and smaller and smaller, dzt does not. dzt is smaller than t. So when t goes all the way down to dt, dzt is not eliminated, but the subtraction wipes it out. So all we're left with is the drift component. Remember, dzt is fractal in dt. So no matter how far you zoom in, it's still going up and down and doing its thing. Now W0 is an initial condition, which means we love initial conditions because we get to define them, and I choose 0. So our problem now becomes just this. Maximize the drift. Maximize the drift with respect to our portfolio allocation at every instant t. So in the next video, I'll actually do it, and I'll see you there. Thank you.